Module 3, Lecture A, Collections for Engineers. By the end of this lecture, you will be able to use lists and tuples to store ordered electrical measurements and waveform samples, use dictionaries to represent labeled component values, node voltages, and test results, and process collections with indexing, slicing, iteration, and aggregation for engineering summaries. Lists and tuples. Voltage samples. Voltage samples are ordered readings captured over time by tools like multimeters and oscilloscopes. Because their sequence shows how an electrical system changes, lists are useful for storing and analyzing them. For example, morning solar panel readings can reveal rising voltage as sunlight increases. Ordered collections are useful for voltage samples because they preserve both the readings and their sequence. This helps engineers study changes over time, such as circuit responses, supply ripple, or capacitor charging. Lists are best when data may need to be added or corrected during an experiment, while tuples are better for finalized records that should remain unchanged. In engineering workflows, choosing a list or a tuple shows how the data should be treated. A list suggests voltage data is still being updated during analysis or testing, while a tuple signals a finalized, stable record for comparison or documentation. In both cases, preserving order is important for tracking trends, finding anomalies, and judging system performance and safety. Python code, voltage samples. Lists keep voltage samples in sequence, while tuples preserve completed waveform records without change. Indexing and slicing help summarize key signal behavior from those stored samples. A list is created to store voltage samples, making the measurements easy to update as data changes. This flexible structure supports adding, removing, or correcting values during real-time data collection and analysis. A new voltage sample is added to the existing measurements so the data stays current. This keeps the collection of readings up to date and ready for later analysis or processing. The second voltage sample is corrected to 1.22 after recalibrating the measurement probe. This keeps the data accurate and reliable for later analysis. Convert the changeable list of voltage samples into a tuple to make the readings immutable. This locks in the completed waveform data, helping prevent accidental changes during later analysis or reporting. We examine key parts of a tuple of voltage samples by taking the first value as the starting measurement, the last value as the final measurement, and a small middle slice from the third through fifth values. Together, these selections help compare the overall voltage change and inspect a focused section of the data for patterns or anomalies. Compute 3 key voltage measures from the final trace: the average voltage, found by averaging all samples, the peak voltage, found as the highest recorded value, and the voltage rise, found by comparing the last sample with the first. Together, these describe the typical level, maximum level, and overall change in the voltage signal. The program first shows the editable voltage samples, then converts the completed readings into an immutable tuple called the final trace. It summarizes the data by reporting the first and last samples, a middle slice of the waveform, the average voltage rounded to 2 decimal places, the peak voltage, and the total rise from start to finish. Together, these printed results give learners a concise overview of the voltage readings. The script stores voltage readings in a list so they can be updated, then converts the final data into an immutable tuple to preserve the recorded samples. It extracts the first, last, and middle readings, then summarizes the waveform by finding the average voltage, peak voltage, and total rise from start to finish. The result is a concise example of managing and analyzing voltage sample data. Fixed waveform samples. Waveform samples are captured at regular time intervals, so their order must be preserved because each sample represents the signal at a specific moment. Changing that order would change the waveform's behavior. Lists are useful when the sample data may need editing or extension, while tuples are better for storing validated waveform segments that should remain fixed, such as a reference cycle for later comparison. Fixed waveform samples are important because they provide stable reference patterns for comparison, calibration, or control. Engineers may store captured signals from lab equipment, use fixed patterns in embedded systems, or analyze switching waveforms in power electronics. Keeping the samples in order preserves their timing context, creating a compact record of how the signal behaves over time. Choose between a list and a tuple based on how the waveform samples will be used. Use a list while measurements are still being adjusted, such as correcting offsets or removing noise. Once the waveform is validated as a fixed reference, use a tuple to prevent accidental changes and make its meaning clear. In both cases, keeping the samples ordered preserves the time structure needed to understand the signal. Python code, fixed waveform samples. Waveform samples can be stored in ordered collections, so each sample has a clear position. Use mutable lists when the samples may change, and stable tuples when the sample set should stay fixed. For fixed samples, simple indexing is enough to access and summarize the data. We define a mutable list of oscilloscope voltage samples to represent a waveform over time. The values include both positive and negative readings, showing how the signal moves above and below zero. This gives us waveform data that can be changed and analyzed in later steps. Set the voltage offset to 0.05 to correct small probe-related errors in waveform measurements. This adjustment helps make the recorded voltage readings more accurate. A new corrected list is created by adjusting each sample for the probe offset. Each voltage value has 0.05 volts subtracted, then is rounded to 2 decimal places. This produces corrected measurements that better reflect the intended voltages. The corrected voltage samples are converted into a tuple to make the reference waveform immutable. This keeps the data stable and helps prevent accidental changes during later processing. The code expects each waveform cycle to contain 8 samples. This expected count is used later to check whether the actual sample count matches, helping confirm the waveform data is complete and consistent. First, the reference tuple length is checked against the expected sample count to confirm the waveform record is complete. If the counts match, the status message notes that the data matches the expected one-cycle record, confirming it is ready for further analysis. In the else block, the code shows a status message when the waveform's sample count does not match the expected one-cycle record. This alerts the user to a possible data consistency issue that must be checked before analysis. We summarize the waveform by taking its first sample as the initial value, then finding the highest and lowest samples. Together, these values show the waveform's starting point and its overall range of voltage variation. We extract the first 4 values from the waveform data to isolate its positive half cycle. This focuses the analysis on the waveform's initial rise and peak, which are key features in understanding the signal's early behavior. The average voltage is found by adding all samples in the reference tuple and dividing by the number of samples, giving the mean value over one waveform cycle. The peak-to-peak voltage is the difference between the highest and lowest sample values, showing the waveform's full voltage range. The output summarizes key checks and measurements for a corrected waveform. It first shows the original samples, then the adjusted immutable waveform, along with a status message confirming whether the sample count matches one cycle. It also reports the first corrected voltage, the positive half cycle, the average voltage rounded to 3 decimals, and the peak-to-peak voltage as a measure of amplitude. This script analyzes oscilloscope voltage samples by correcting them for probe offset and storing the adjusted waveform as a fixed reference. It verifies that the sample count matches the expected value, then reports key waveform features such as the first value, peak, minimum, positive half cycle, average voltage, and peak-to-peak difference. The printed output gives a concise summary of the waveform and its main characteristics. Current samples. Current samples are often best stored as ordered collections because their sequence carries important meaning. In engineering, the position of each measurement can show initial conditions, rapid transitions, or steady behavior during events such as motor starts, battery discharges, transformer inrush, or power converter switching. Keeping the data in order helps engineers recognize patterns and connect changing current values to the behavior of the physical device. Use tuples when data should not change after it is created, such as calibrated readings or a fixed test waveform. Use lists while data is still being collected or updated during a test. After collection is complete, converting the data to a tuple helps protect its integrity and supports consistent, reliable analysis. Engineers use ordered collections of current samples to keep electrical data tied to its context, such as time intervals or load levels. Organized as lists or tuples, these samples make it easier to interpret changes, find peak currents, and compare operating phases. This gives engineers a compact but useful way to analyze electrical system behavior. Python code, current samples. Use ordered collections to store current samples. Lists are useful when laboratory measurements may keep growing, while tuples are better for protecting approved reference sample sets from change. We create a list to store motor current measurements in amperes. Using a list makes it easy to add or update values as testing continues, which is useful when experiments collect data dynamically. A tuple stores the approved baseline current values, so they remain unchanged after being set. This immutability protects the reference data and supports consistent comparisons during analysis. Check whether the current samples and baseline currents contain the same number of values. The result is a true or false value that shows if their lengths match. This matters because later element-by-element comparisons or calculations only work correctly when both collections are the same size. A new motor current reading is added to the measured currents list using the append method. This lets the list grow as tests run, making it easy to capture real-time data without setting the list size in advance. We select the first 3 current measurements to examine the motor's early transient response. This focuses the analysis on the initial readings, which can reveal important startup behavior. Simple engineering summaries of current data use 2 key values, the peak current and the average current. The peak is the highest measured sample, while the average is found by adding all samples and dividing by how many there are. Together, these give a quick overview of the current measurements. Before comparing peak currents, we first confirm that the measured and baseline data have the same number of samples. If they match, we use the maximum function to find the baseline peak. If they do not match, the baseline peak is set to none, showing that a valid comparison cannot be made. The output summarizes measured current data and compares it with approved baseline values. It shows the collected samples, the reference currents, and the early transient readings, then reports the measured peak and the average current rounded to 3 decimal places. It also verifies whether the measured sample count matches the baseline count, and only then reports the baseline peak for a safe comparison. This script analyzes motor current data by keeping measured samples in a flexible list and baseline values in a fixed reference collection. It checks whether the two sets have matching sample counts, adds a new measurement, and reviews the first few readings to capture early behavior. It then calculates key performance values, including the measured peak and average current, and safely compares the baseline peak when the counts match. The overall goal is to support reliable engineering analysis through simple data checks and summary statistics. Engineering dictionaries. Component value maps. A component value map connects each circuit label, such as R1 or C1, to its actual value, such as a resistance or capacitance. By using the same labels across the schematic, bill of materials, and hardware, engineers can keep design data aligned with real components. This reduces ambiguity and makes the engineering process clearer and more efficient. As a design grows, a component value map helps keep each part's value tied to its meaning. In a power supply, labels for feedback resistors, output capacitors, or switching inductors can be stored with their values in a dictionary. This makes the design easier to check, update, and connect to other tools, unlike an unlabeled sequence where the position of each value must be remembered separately. Component value maps help teams communicate and verify circuit information across design, troubleshooting, and production. They connect component values and ratings to designators, making it easier to compare designs with recommendations, measurements, or inspection results. By preserving the meaning of the data, they help identify issues such as repeated failures or incorrect substitutions. Python code, component value maps. Dictionaries connect component labels to their engineering values, keeping the meaning of a schematic clear. When these maps are small, they are also easy to review and verify. Create a component values dictionary to connect schematic labels, such as R1 and R2, with their engineering values, such as 10 kiloohms or 2.2 kiloohms. This makes each component easy to reference and helps keep the schematic clear and meaningful. The circuit uses a dictionary to match component labels with their values. It assigns one capacitor a value of 100 nanofarads, another capacitor 10 microfarads, and an inductor 47 microhenries. This keeps the circuit design clear and organized by linking each part to its engineering value. The component value dictionary links the diode label D1 to the part number 1N4148. This makes the schematic clearer by connecting each label to its specific component value. To access a component's specification, select its label in the dictionary. In this case, the label C1 refers to a capacitor, and looking it up returns the capacitor's value. This makes the component's value easy to use in later operations or analysis. After the design review, the resistor labeled R2 is updated to 2 kiloohms in the component values dictionary. This keeps the dictionary aligned with the revised schematic and current design specifications. A new component is added to the component values dictionary. The identifier U1 is linked to the LM358 op amp, helping the design track that component and its type. Use the length function on the component values dictionary to find how many components are defined. This counts all key value pairs, giving a quick measure of the size of the component map without manual counting. Component labels can be grouped by checking the first character of each dictionary key. Labels that start with R are collected as resistors, while labels that start with C are collected as capacitors. This simple filtering approach organizes components by type, so they are easier to manage and analyze later. This example prints a brief component value map summary. It shows the selected value for capacitor C1, the updated value for resistor R2 after review changes, and the total number of labeled components by counting the dictionary entries. The code sorts the component labels alphabetically, then goes through each one and prints its corresponding value. This creates a clear, organized display of all component values for easy review. The code groups components by their label prefixes. It prints labels starting with R, typically resistors, and labels starting with C, typically capacitors. This makes it easier to identify component types quickly. This script manages an inventory of electronic components stored as label and value pairs. It retrieves a capacitor value, updates a resistor, adds an operational amplifier, then counts and groups components by type. Finally, it prints a concise inventory summary, including key updated values, the total number of components, an alphabetical component list, and grouped resistor and capacitor labels. Node voltage maps. A node voltage map links each circuit point to its voltage using clear labels such as input, output, and ground. This makes it easy to see which voltage belongs to each part of the circuit and avoids confusion from unlabeled sequences. It also makes circuit data simpler to review, interpret, and share. Node voltage maps help engineers organize voltage data from simulations, measurements, and diagnostics. By using clear node names, they create a snapshot of how a circuit is behaving, making it easier to compare expected and actual values or check control signals. In systems such as power supplies, microcontrollers, and renewable energy setups, these labels keep measurements aligned with the circuit's intended meaning. Node voltage maps help make circuit analysis clearer by linking each measured voltage to a meaningful label. This makes it easier to compare results across loads, operating conditions, or repeated lab measurements. By preserving context, these maps support quick checks of supply rails, feedback nodes, anomalies, and report summaries. Python code. Node voltage maps. Dictionaries can label circuit node voltages by using node names as keys and voltage readings as values. This helps engineers summarize and organize node data clearly. Create a dictionary to store circuit node voltages using clear labels like input and regulator output for each node. This makes it easy to find and manage the voltage readings for different parts of the circuit. The dictionary stores key circuit node voltages for later use in the code. It sets the feedback node to 1.24 volts, the sensor line node to 2.72 volts, and ground to 0 volts as the reference level. The code reads key circuit voltages from the stored node values, the regulator output, ground, and input. The output voltage helps evaluate regulator performance, ground provides the reference level, and the input voltage supports calculating the voltage drop across the load to assess efficiency. The code summarizes key circuit voltages by finding the load voltage drop from input to output, measuring the sensor line voltage relative to ground, and then displaying the full node voltage map. Together, These values give a concise view of voltage loss, sensor behavior, and overall circuit node voltages. The code reports three key circuit voltages: the regulator output voltage, the input-to-output voltage drop, and the sensor line voltage above ground. The calculated differences are rounded to 2 decimal places and printed in volts, giving engineers a quick view of the circuit's important voltage relationships. The acceptable output voltage is defined as a range from 4.75 to 5.25 volts. The actual voltage is then checked against these limits, and the result indicates whether it is within range or outside the allowed tolerance. The code verifies whether the regulator output voltage stays within the allowed tolerance and reports if it is acceptable. It also counts how many node voltage readings are stored in the voltage map, and prints that total as a quick overview of the tracked nodes. The code gives a quick summary of node voltages by calculating their average. It adds all stored voltage values, divides by the number of nodes, and prints the result rounded to 2 decimal places. This script summarizes circuit node voltages by storing each node's reading, calculating important voltage differences, and checking whether the regulator output stays within its allowed tolerance. It reports the node voltage map, selected voltage values, the input-to-output drop, and the regulator status. It also counts the nodes and computes the average voltage to give a concise overview of the circuit's voltage behavior. Measured test results. Engineering test results are best stored in dictionaries because each value is tied to a clear label, making the data meaningful and easy to find. Measurements depend on test conditions and standards, so names like output voltage or input current help engineers interpret results by purpose rather than position. This makes dictionaries useful for organizing varied data, such as voltage, current, temperature, and pass status, into a complete test record. In engineering, dictionaries help organize test results by attaching clear labels to each measurement, such as voltage, ripple, offset, or noise. This makes data easier to read, trace, share between programs, and save for later analysis. Because the meaning of each value is explicit, dictionaries reduce confusion and support clearer analysis of complex data. Dictionaries help organize engineering test data by connecting each measurement to a clear label, such as a condition, category, or serial number. This makes it easier to compare results across scenarios and track outcomes in production. Overall, dictionaries improve the clarity, traceability, and communication of test results. Python code measured test results. Dictionaries are useful for labeling measured electrical test results. Their keys name what each measurement represents, rather than where it is stored, and their values can hold different engineering data types. A test result dictionary stores one bench test record using descriptive labels for each measurement. In this example, it records the unit serial number as PSU 042, the output voltage as 5.08 volts, and the input current as 312 milliamps. This keeps the key test data organized and easy to access. The power supply shows a ripple voltage of 18.5 millivolts peak to peak, a case temperature of 41.2 degrees Celsius, and a switching frequency of 501 kHz. It also passed the visual inspection, indicating acceptable physical quality. A dictionary of limits stores the acceptable ranges for each measurement, such as output voltage, ripple, and case temperature. Each measurement label maps to its allowed minimum and maximum value. For example, about 5 volts for output voltage, up to 25 millivolts peak-to-peak for ripple, and 0 to 70 degrees Celsius for case temperature. These predefined ranges make it easy to check whether measured values are within specification. The validation first compares the required measurement keys with the keys found in the test results. Any required key that is absent is treated as missing. An assertion then checks that nothing is missing and raises an error if a required measured value is not available. This ensures all necessary measurements exist before further validation continues. The process creates a results dictionary to track whether each measurement passes its limits. It goes through the stored limits, gets the lower and upper bound for each measurement, then compares the corresponding measured value against those bounds. Each comparison produces a true or false result, which is saved for that measurement, so the final record shows which measurements are within their acceptable range. The test first confirms that every electrical check has passed, meaning all measured values are within their required limits. It then determines the overall result by combining this electrical status with the visual inspection result. The unit only passes overall if both the visual inspection and the electrical limits pass. The output prints a short summary of measured test results for a specific unit. It identifies the unit by its serial number, then reports the output voltage in volts and the ripple measurement in millivolts peak to peak. The code reviews each measurement's limit check result and labels it as pass or fail. It then prints the measurement name with its status, giving a concise summary of which measurements met their limits. The code prints whether the unit passed all checks. It reads the overall pass value from the test result data and displays it with a clear label, giving a quick summary of the test outcome. This script reviews electrical test results for a power supply unit by comparing required measurements, such as voltage, current, and ripple, against acceptable limits. It confirms the needed data is present, checks each value, and combines those results with a visual inspection status. The output is a concise report showing the unit's serial number, key measurements, individual pass results, and overall pass or fail status. Processing, signal collections. Signal slicing means selecting only the part of a signal that matters for analysis, instead of working with the entire data sequence. Engineers use it to focus on meaningful intervals, such as a brief response after a change or a steady-state period. This makes it easier to inspect, plot, compare, and summarize relevant samples without unrelated data getting in the way. Signal slicing means selecting specific sample positions from a dataset, often corresponding to a time range or operating condition. In sampled waveforms, this lets engineers focus on the part of the signal that matches the event being studied, such as early contact bounce or later stable operation in a relay test. By isolating these segments, you can compute useful measures like overshoot or average voltage, while excluding irrelevant data such as startup noise. Signal slicing lets engineers compare the same portion of data across different tests or conditions. By choosing equivalent segments, such as the response after a step input, summaries like averages, peaks, or settling behavior become more consistent and meaningful. Good slicing is not just a processing step. It should be chosen carefully to reflect the physical behavior of the system. Python code. Signal slicing. Signal slices focus on the meaningful parts of a waveform, so engineers can summarize selected samples instead of analyzing every point. This example uses simple voltage samples to illustrate the idea. We store oscilloscope voltage samples in order, with each value representing the signal at a different time. Keeping the samples in a list makes them easy to access and analyze, especially when focusing on parts of the waveform, such as transient and steady-state regions. The code defines a sequence of oscilloscope voltage samples that describe how a waveform changes over time. The values vary slightly around 5 volts, with one higher reading and one lower reading, and they form part of a larger dataset used to study signal phases such as transient and steady-state behavior. Before slicing the voltage data, we check that the dataset contains the expected 12 samples. We compare this expected count with the actual number of stored samples, and an assertion stops execution if they do not match. This helps catch missing or extra data before further processing. The voltage samples are narrowed to the transient region, where the signal changes after switching begins, by selecting samples 2 through 6. Within this slice, the peak voltage is found using the maximum value, and the average voltage is calculated by summing the selected samples and dividing by their count. To analyze steady-state behavior, use the voltage samples starting from the 7th sample after the system has settled. Then find the average voltage in this region to estimate the typical steady operating level, and identify the minimum voltage to see the lowest point reached during steady state. This analysis summarizes voltage samples by separating the signal into transient and steady-state periods. It first reports the total sample count, then examines the transient window by identifying its peak voltage and average voltage. It also reviews the steady-state window after the system has settled, reporting its average voltage and minimum voltage. Together, these values give a compact view of the signal's early response and stable operating behavior. This script analyzes oscilloscope voltage samples by first confirming the expected sample count, then focusing on separate transient and steady-state regions. In the transient region, it finds the peak voltage and average voltage. In the steady-state region, it calculates the average voltage and minimum voltage. The printed results summarize the key waveform behavior without requiring analysis of the full dataset. Looping signal samples. Engineers iterate through signal samples to turn stored measurements into useful observations. Because readings are ordered over time, they can be checked for limits, analyzed for behavior, or prepared for further processing. This is similar to how sensors produce continuous streams of data, where patterns such as spikes or noise can reveal stress, faults, or interference. Signal samples are meaningful only when their measured value is considered together with their position in the sequence. The value shows what was measured, while the position connects it to a time or event. By looping through samples, engineers can apply consistent checks across large datasets, such as finding threshold violations or detecting unusual waveform behavior. Iteration lets engineers scan large signal datasets and turn raw samples into useful summaries. By checking each sample, they can track overall levels, threshold violations, and extreme values to judge system performance and stability. This is especially useful in automated validation, where software quickly flags issues and supports reliable reports for tests such as batteries or environmental conditions. Python code, looping signal samples. Loop through signal samples carefully, keeping track of each sample's position and value. Summarize the results clearly and keep the output brief so learners can focus on the main information. First, we create a voltage samples list to store voltage readings in order. These readings represent measurements from different times or locations and will be used to check for safety violations and calculate summary statistics. A 5-volt safety threshold is set to check whether any voltage sample is too high. This limit helps identify samples that may be unsafe and need to be handled during processing. Before processing the voltage samples, two tracking values are initialized. One counts how many readings exceed the safety threshold, and the other stores the running total of all readings. Together, these allow the loop to detect violations and calculate the average voltage afterward. We loop through the voltage samples using the enumerate function to access each sample's position and value. As each reading is processed, its voltage is added to a running total. This total will be used to calculate the average voltage across all samples. The code compares each voltage sample with a safety limit. When a sample is above that limit, it adds 1 to the violation count, helping track unsafe readings for review. The code reports when a voltage sample is above the safety limit. It identifies the sample by number and shows its voltage rounded to 2 decimal places, making it easier to spot problematic readings during analysis. Average voltage is found by dividing the total of all voltage samples by the number of samples, giving a typical value for the dataset. The maximum voltage is the highest sample value, showing the peak level recorded and helping describe the data's range. The output summarizes the voltage data by showing how many samples were checked, the average voltage, and the maximum voltage recorded. It also reports how many samples exceeded the preset voltage limit, highlighting any safety threshold violations. The script checks voltage samples against a 5-volt safety limit, while also tracking the total voltage and the number of violations. It reports any sample that exceeds the limit, then summarizes the data by showing the average voltage, maximum voltage, and total violations. This gives a concise view of whether the measurements meet the safety standard. Batch signal summaries. Batch signal summaries reduce large measurement sets into key values that describe overall signal behavior. They help engineers quickly see averages, extreme spikes, and threshold breaches from oscilloscope or simulation data. This makes it easier to judge issues such as regulator stability or signal amplitude limits without reviewing every data point. A batch summary should begin with a clear question about the signal and the engineering decision it supports. Whether analyzing battery discharge or motor vibration, the goal is to process samples through iteration and aggregation to compute useful results such as extremes, averages, counts, or threshold rates. This turns raw data into actionable summaries for diagnosis and reporting, rather than simply storing it for later. Batch summaries help compare many signals or device measurements quickly, such as checking circuit boards, daily power use, or lab waveforms under different conditions. They make patterns like outliers, peaks, averages, and component effects easier to see. However, because summaries compress the data, they can hide details such as noise or faults, so they should support analysis rather than replace a full understanding of the signal. Python code batch signal summaries. Signal samples can be summarized in batches to support faster analysis. Lists store ordered voltage measurements, and aggregating those values helps engineers make quick decisions. 2 ordered lists are created to store batches of voltage measurements, one for a 5-volt rail and one for a 3.3-volt rail. Each contains 6 readings and will be used later to summarize the signal characteristics of each rail. The voltage readings are organized into named groups for each power rail, making each batch easy to access and analyze. A separate set of safe voltage limits is defined for those rails, so readings can be checked against their thresholds. An empty results list is then prepared to store each batch's average, maximum, minimum, and the number of readings above the safe limit. The code goes through each signal and its voltage samples, then counts how many samples are in that batch. It checks that every signal has at least one sample, ensuring there is data available before later processing continues. To summarize a batch of signal samples, calculate the average to estimate the typical voltage, then identify the highest and lowest measurements. Together, these values describe the signal's central tendency and range. For each signal, the safe limit is retrieved and the samples are checked to count how many exceeded. The final summary records the signal name, average, highest and lowest values, and the number of samples above the limit. This gives a compact overview of the signal's key measurements and any safety exceedances. The output begins with a header introducing the batch signal summaries. It then goes through each summary entry and prints a compact report for each signal, including its name, average voltage rounded to 2 decimal places, maximum and minimum voltage, and how many samples exceeded the safe limit. This gives a quick overview of key signal behavior for analysis. A small time window of voltage samples is selected from the Rail A voltage list using slicing. The selected values are averaged by adding them together and dividing by the number of samples. The result is then printed to 2 decimal places as a concise summary of the voltage during that period. The script analyzes voltage samples from 5-volt and 3.3-volt rails. For each rail, it reports the average, highest, and lowest voltage and counts samples that exceed safe limits. It also checks a small time window in the 5-volt rail by averaging samples 2 through 4, giving a quick summary of signal behavior for engineering review. In this lecture, you learn to use lists and tuples to store ordered electrical measurements and waveform samples. Use dictionaries to represent labeled component values, node voltages, and test results. And process collections with indexing, slicing, iteration, and aggregation for engineering summaries. In the next lecture, Lecture B, we will go over files and reports. Thank you for your attention. See you all in the next lecture.